Hello everyone, my name is Adwait Deshpande and I am a PhD student in electrical and computer engineering at the University of Utah. It is with great pleasure that I present my research today with everyone present at the IEEE FLEPS conference. Over the next few minutes, I will be talking about how to increase the adhesion strength of PDMS bonded to polyimide with thin film silicon dioxide. This may find several applications in integrating flexible electronics with microfluidic systems. I will be starting with the importance of polyimide and PDMS for flexible systems. Later, I will talk about the need for having a strong bond between polyimide and PDMS. I will then go over the current techniques used for bonding polyimide and PDMS. Further, I will discuss why silicon dioxide is a suitable material for bonding PDMS and polyimide. I will then go into the fabrication process flow. Then I will talk about our experiments and their respective results. Polyimide is one of the most widely used materials in flexible systems. It is used in flexible PCBs or flexible integrated circuits. It is also used as an encapsulation material or as a substrate. It can be used for making sensors, uh, wearable devices, implantable devices, etc. Inclusion of a PDMS substrate adds a stretchable component to flexible systems. PDMS is also the most widely used material for microfluidic systems. Integrating flexible electronics with microfluidics has garnered a lot of interest in the past 2 decades. Common integration techniques involve having electronic components separated from the microfluidic parts. These electronic components could be located in special strain isolation cells and connected to the microfluidic counterpart by liquid metal traces. Conversely, the microfluidic channels in PDMS bonded to a glass substrate could be soldered onto a flexible PCB and glued together, as shown by Furniturewala et al. However, selective bonding of PDMS-based microfluidics to polyimide-based flexible electronics is still a challenge. Direct bonding of polyimide and PDMS results in poor adhesion between the two. Plasma treatment alone or combined with other chemical treatments are used for improving the adhesion strength of the bond between PDMS and polyimide. Some chemicals used in literature are APTES, MPS, butyl rubber, epoxies, etc. Surface treatment with a combination of MPTMS and GPTMS followed by plasma treatment produces the best bond strength of 460 newtons per meter as found in literature. However, in these methods, the entire surface has to be exposed to these surface chemical treatments. This may not be desirable for some sensitive devices. Also, these treatments do not allow selective bonding of polyimide and PDMS. In our approach, we use an interfacial SiO2 thin film for bonding PDMS and polyimide layers. SiO2 can be deposited using typical CMOS processes and is photopatternable, and hence selective bonding is possible. Additionally, bonding between plasma-treated PDMS and glass has been widely studied. There exists a strong bond between bonded PDMS and glass. This is due to the formation of SiOH bonds on the surface of PDMS and glass after plasma treatments and conversion of those bonds to SiO-Si bonds after bonding. This results in higher adhesion. Moving on to the fabrication process. For preparing the PDMS slab, a microscope glass slide was first coated with fluoropyl to facilitate easy release of PDMS. An acrylic mold was then glued on to the coated glass slide. Silgard 184 PDMS was mixed in the ratio of 10 to 1, degassed, and then poured in the mold. PDMS was cured at 120 degrees Celsius for 1 hour and then peeled off from the mold. The following steps were followed to create the SiO2 deposited polyimide samples. Photoresist was spin coated on a glass slide and then a non-adhesive Kapton was attached to it. This Kapton was 12.2 mm wide and 25.4 micrometers thick. This photoresist acted as a temporary adhesive layer. SiO2 was then deposited on top of Kapton using one of three methods: atomic layer deposition, plasma enhanced chemical vapor deposition, and sputter deposition. Three different thicknesses were deposited for each type. For ALD, those were 5, 10, and 15 nanometers. For PECVD, they were 50, 95, and 150 nanometers. And for sputtered SiO2, they were 80, 350, and 545 nanometers. PDMS and the SiO2 side of Kapton were treated with atmospheric plasma for 2 minutes and immediately brought in contact with each other. This stack was then pressed and heated at 120 degrees Celsius for 2 hours to allow the bond to strengthen. Control samples did not have any SiO2 deposited. They were, however, plasma treated and then pressed together and heated for 120 degrees Celsius for 2 hours for bonding. The samples can be removed easily from the glass slides with a gentle tug. 5 samples for each thickness for each deposition type were measured. Different methods to analyze the bond strength by peel testing are shown. In our experiment, we have used the 90-degree peel test. Bond strength was calculated by dividing the peak peel force with the width of the peeled Kapton film. From this pull testing setup, we can see that the PDMS block is clamped to the bottom and the overhang of the bonded SiO2 coated polyimide is pulled vertically. The force gauge was configured to measure the peak peel force. Moving on to the results. Two different failure modes were observed: adhesive failure and cohesive failure. In cohesive failure, the PDMS ruptured before the polyimide PDMS interface, indicating that a strong bond was formed. In adhesive failure, the PDMS did not rupture and hence the bond was considered weak. All the samples for all three thicknesses of SiO2 deposited using ALD showed adhesive failures and bond strengths lower than control samples. The bond strength of the control sample was 71 newtons per meter, excuse me. The bond strength for 5 nanometer, 10 nanometer, and 15 nanometer samples were 7 Newton per meter, 10 Newton per meter, and 12 Newtons per meter, respectively. All the samples featuring PECVD 50 nanometers of SiO2 showed adhesive failures, whereas all the samples for other two thicknesses showed cohesive failures. For 50 nanometers, 95 nanometers, and 150 nanometers, the peel strengths were 79 newtons per meter, 125 newtons per meter, and 179 newtons per meter, respectively. All the samples featuring sputtered SiO2 exhibited cohesive failures. Samples with 545 nanometers of sputtered SiO2 exhibited average peel strengths of about twice as much as that of highest value reported in literature. To summarize, all the ALD SiO2 samples and 50 nanometer PECVD SiO2 samples resulted in adhesive failures. All other PECVD SiO2 samples and all sputtered SiO2 samples underwent cohesive failures. Rupturing of the PDMS, that is cohesive failure, indicates that the bond strength is or may be higher than the measured peel strength. 545 nanometers of sputtered SiO2 showed average peel strengths twice as high as reported in literature. Therefore, thin film SiO2 mediated bonding of polyimide and PDMS is an attractive option for realizing flexible microfluidic systems. All the work was performed at the Utah Nanofab in University of Utah, and this work was sponsored by NSF CPS grant. Thank you so much for listening to my talk.